I forgot another cosine theta d theta for substituting the dx. Now what we can do is we can change the bounds. So when x equals 0, sine is going to equal 0. So that's going to stay the same. And when x equals 1, sine of what is 1? That would be pi over 2. Sine cubed theta cosine squared theta d theta. Now we're just going to do what's it called? Basically trig substitutions or trig integrals. I think it's chapter 7.2. Okay, so what we can do is we can take the derivative, or we can substitute u for cosine theta. So du is going to give us negative sine theta d theta, because the derivative of cosine is negative sine. We'll take the negative out. And then we'll plug our things back in. And what we're going to do is the goal is to get sine theta d theta. So we have 0, pi over 2. And we can substitute sine cubed theta for a sine theta and a sine squared theta, or a 1 minus cosine squared theta. And then cosine squared theta d theta. So now we have our sine theta d theta, and we have everything else in terms of cosine or terms of u. So we have 0 to 1 or to pi over 2. Pull the negative out. Sine theta d theta is going to give us negative du, so we'll have du in there. Then we'll just have 1 minus u squared times u squared du. And here we can change the bounds once again. So cosine of 0 is going to give us 1. And cosine of pi over 2 is going to give us 0. So we have the bounds from 0 to 1 of 1 minus u squared times u squared du. Now we're just going to distribute the u squared and take the integral of it. So what we're going to have is negative 0, or 1 to 0 of u squared minus u to the 4th, which is going to give us u cubed over 3 minus u to the 5th over 5 integrated between 1 and 0. And can't forget our negative. And after we do all that, we're going to get, our final answer is going to be 2/15. So try that out, and that's the correct answer, and see if you can get there. Now the next thing I'm going to do is just show you the other two things, the other two options that we have. So when we have the square root of a number squared plus x squared with respects to integrated with respects to x, we're going to substitute x for a tan theta instead of sine theta. And that's going to give us a dx of a secant squared theta d theta. And then a radical is going to equal a secant theta. And you're just going to basically follow the same steps and do trig integrals after you substitute everything in, and you're going to try and simplify, and remember to change your bounds. And then our last kind would be x squared minus a squared with respects to x. we're going to substitute x for a secant theta. So dx is going to give us a secant theta tan theta d theta. And our radical is going to give us a tan theta. Okay, so one last thing I want to share with you is, so what do we do if we don't have bounds? And we can't change the bounds from x to, to a theta. What we're going to want to do is we're going to want to make a triangle. And each one is going to be different, so we'll take this top one for instance. We have x equals a tan theta. So if we divide by a, we're going to get tan theta equals x over a. So if we make this angle theta, tan theta is opposite over adjacent. So we have opposite, which would be x, over adjacent, which will be a. And then this will always be a radical, and you can solve for it if you don't believe me, but I'll just tell you now. And then we can do that with each of the cases, and what you're going to want to do is, once you substitute all the trig functions back into your integral, and you substitute, simplify, take the integral, what you're going to want to do is you're going to want to take each trig's function that you get and plug it back into this triangle. So if you end up with secant theta, which is 1 over cosine theta, it's going to be adjacent over hypotenuse, so it's going to be hypotenuse over adjacent because it's secant. You'll substitute a secant theta for the radical over a. And then you're going to have c at the end also. Don't forget your c. Alright, well this was trig substitution, and I hope you enjoyed it. Thanks.